Hello, and welcome to Chapter 15, Part 2. In this last part of this chapter's lecture, we will be introducing concept of sound waves. Let's start with the definition of sound. A sound wave is vibrations consisting of compressions and rarefactions traveling through air, water, or solids. Sound waves are produced by vibrating objects. For example, a tuning fork is a piece of metal here, and if we strike it with a hammer, it vibrates back and forth. What happens is as it vibrates back and forth, it compresses the air molecules next to it every time it moves to the right, and it creates a region of higher pressure, which is called a compression. When the tuning fork moves to the left, it leaves a region where there are less air molecules and lower pressure, and this is called a rarefaction. And these compressions and rarefactions travel away from the tuning fork at the speed of sound. We'll see an animation of this on the next slide that will help clarify what's going on here. One way we can plot this is a plot of pressure versus position. And so in these compression regions here, we see the pressure is high. So that's these peaks here on our graph. And then in between the compressions are the rarefactions where the pressure is lower, and those are represented by the troughs in the graph. So this graph here looks very much like the graph that we saw in part 1 of the video when we looked at, for example, waves on a string. So mathematically it has a very similar form and properties in terms of the wave. The speed of sound, so how fast do these compressions and rarefactions move? Well, this is called the speed of sound. So in air at room temperature and sea level, the speed of sound is about 340 meters per second. In water, since the water molecules are closer together than they are in air, the sound can transfer from molecule to molecule much more quickly. Therefore, the speed of sound in water is much higher. It's about 1,500 meters per second. And if we go to a solid like steel, again, the steel or iron atoms are very closely packed and they're held together by strong bonds. So any vibrations in those atoms can be transferred to their neighbors very, very quickly, resulting in a much, much higher speed of sound, and we see it's somewhere around the order of 5,000 meters per second. So this is a nice animation that shows how sound waves are produced and how they travel. And this is kind of fascinating here. What this is showing is we've got a tube or a pipe just filled with air molecules. All these little black dots represent individual air molecules. Over here is a plunger or a piston that is moving back and forth, creating some frequency of sound. And you can see whenever it moves to the right, it pushes the molecules towards each other and makes a compression. One of these regions where you see it darker, where there are more air molecules closely spaced together. When the piston moves back to the left, like right now, you can see it leaves a rarefaction, a region where there's more space and less pressure between the air molecules. Now, one thing we notice here is that these compressions are moving to the right, and they're moving at the speed of sound. This is in slow motion, of course. But remember that the individual molecules are not moving from one end of this pipe to another. In fact, if you look at these red tracer molecules, there's one here, here, and over here. If you watch what happens to them, they simply move back and forth, left to right. They stay in the same place in general. They just move back and forth as the wave passes through them. So sound waves, just like any wave, it passes through the air. It doesn't carry air with it. Now, this is a longitudinal wave because the air molecules are vibrating back and forth in the same direction that the wave is traveling, which is horizontal in this picture here. Down here is a plot of sound pressure, and you can see that these regions of high pressure here, the compressions, are represented by the peaks here. And so we see the peaks and the troughs moving to the right, and we can define the wavelength of sound as the distance between two adjacent peaks. In order to better understand how sound is produced, let's take a look at how a loudspeaker works. So speakers are found in radios, stereos, TVs. Your cell phone has a speaker in it, obviously when you press the speaker button, or when you hold it up to your ear, there's a tiny speaker in there as well, and as well as headphones, earbuds, speakers are found, in anything pretty much that produces sound. So the way it works is actually quite simple. There is what's called a speaker cone here, which is either made of paper or plastic, and it is attached to a coil of wire that leads to the source of the sound, which is some electrical signal. There's also a magnet inside the speaker here, and what happens is, and this is something we'll learn about later, in the course if you study electricity and magnetism, is when electric current flows through the wires here, it creates a magnetic field, and that either is attracted or repelled to this magnet here. So if the sound signal here is varying at, let's say, 400 hertz, 400 cycles per second, what happens is this speaker cone is going to move back and forth at 400 cycles per second, 400 times per second, and it's going to produce a sound wave with that same frequency, because remember, as it moves back and forth, it's going to compress the air molecules in front of it 400 times a second. Here you can see in this animation, the speaker is actually moving back and forth, with some signal that's fed into the coil here. So what we're going to do shortly here is we will listen to some different frequencies and see how our ears and our brain interpret that sound. So this has to do with what we call pitch, and pitch is basically a musical term that determines how high or low a sound is on the musical scale, and pitch is all about the frequency of the sound. So let's start here by listening to sounds at different frequencies in a video simulation demonstration. This is an online tone generator that creates a musical tone or pitch where we can control the frequency, which is shown right here. So I'm going to start here at a frequency of 200 hertz, and let me turn up the volume here so you can hear this. So what's happening at this frequency is the speaker inside the computer, and also the speaker inside the device that you're listening to right now, is vibrating back and forth 200 times per second to produce this pitch. Now watch what happens as I reduce the frequency. So now we've gotten to such a low frequency that we basically don't hear it anymore. It's just vibrations once we get down here below about 20 hertz. But let's go up now and listen to it as we increase the frequency to higher and higher frequencies. Turn down the volume a little bit because it starts to get really loud. The higher frequencies have a lot more energy than the lower frequencies. So here we're at about 750 hertz. This is 1000 hertz right here. There's 1000 hertz. And I can double it by hitting this button here. This goes up, that's called an octave in music. Let's go to 2000 hertz. And here's 4000. 10,000 now. And I can keep going up now. Once we get above 10,000, interestingly, my hearing starts to fail, and I can't really hear the pitch. But you guys probably can still hear this at home. I'll turn up the volume a little bit for you. And depending on the speakers, you may or may not be able to hear this as I go to 11,000, 12,000, 15,000 hertz. And the upper end of human hearing is usually considered around here at 20,000 hertz. Now we can go back down. So that is the effect of different frequencies. It produces a different musical pitch. If you want to play around with this tone generator, you can see the URL right up here, and you can pull this up on your device and test your hearing and see what your ears hear at different frequencies. So you just got to hear the effect of different frequencies and how it makes different pitches that we hear with our ears. And it's interesting to see that the range of hearing depends quite a bit on the species of animal. For example, elephants with their larger ear structures can hear only lower frequency sounds up to about 12,000 hertz, and they can apparently hear subsonic sounds that we would not be able to hear. Our hearing goes from typically about 20 hertz to about 20,000 hertz for a young, healthy person. As you get older, we start to lose the upper part of the spectrum of sound. As I mentioned during the demonstration that we just heard, I can only hear sounds up to about 10,000 hertz because I'm a little bit older than you guys. I think even younger kids than you can hear the full range of sound here. But it's interesting to look at some of these other species. For example, dogs, as you probably have heard, they can hear sounds much higher in frequency and pitch than the human ear can. And so a dog whistle, for example, that are used by the police and the military is a ultrasonic sound that we can't hear, but it's a dog can plainly hear that sound. So the dog whistle is set to some frequency above 20,000 hertz where our ears go to. Look at the mouse. It can hear up to something like 90,000 hertz. I'm guessing that's due to its tiny little bones and structures inside of the tiny mouse's ear that allows it to vibrate faster. But notice that the lower end of the frequency for the mouse is around 1,000. That is a pretty high pitch to you and me, and apparently they can't hear anything lower than that. Bats have interesting hearing senses. We'll talk about their echolocation later, but you can see they also go to extremely high frequencies, as do porpoises. One of the fun things about watching most science fiction movies is the action scenes where there are battles in space and something is blown up, like a spaceship or the Death Star or whatever is blown up, and we hear this tremendous explosion, right? And makes it really exciting. However, that's all bogus, right? There is no sound in space because there is no air in space. Sound requires a medium to transfer through. So in the vacuum of outer space, if something explodes like this, it makes no sound at all. It would be completely silent. There's an interesting way to demonstrate this using what's called a bell jar. And inside this bell jar is actually a bell that will be ringing, and we can pump the air out of this bell jar and listen to the sound become more and more quiet. So I'll have you watch this video demonstration of another instructor that does this demonstration.
Hi, today we're talking to you about pressure and some different experiments we can do with pressure. Here at Rutherford Laboratories, we have received a new affordable bell jar and we will demonstrate a few things with it today. This bell jar sucks out the air from this container, the bell. And so what we will do is demonstrate how sound needs air particles to vibrate in order for you to hear it. This bell makes a sound like this. What we will do is place the bell jar, place the alarm bell in this position. Then we will turn it on. Place the bell jar on top of it. Notice you can still hear it. Now we will turn on the compressor. Oh, not compressor. Vacuum pump. We have a nice vacuum pump. Doesn't make too much noise. And we'll just wait, see what happens. Can you hear any difference? We'll let it run for a minute, and then we'll turn off the compressor so you can really see if there's any difference in the sound. Now I'll turn it off. Oh, I forgot to close the bell jar. Can you hear it getting louder again? Let's turn it on again. Now the important step on this little bell jar, it has a nice valve. So you just turn the valve and it keeps the air from going back in. So I'll do that before I turn off the vacuum pump. Turn off the vacuum pump. Can you hear the bell? Let me give you a close-up look. Can you see it? Can you hear it? Now, watch what happens when I open the valve. Listen. Opening this valve right here. Letting the air in. Can you start to hear it? I do believe you can. It's a very neat property how air is required, some medium, to transfer sound. There are particles that need to be vibrated from the source all the way to your ear. That's it for this video. Check back for more. Signing off, Mr. John.
So the speed of sound that's how fast the sound wave moves through air. And the speed of sound depends on how fast the atoms or molecules in the medium can move and interact with each other. So if we have air at a cold temperature, so 0 degrees Celsius, remember, is the freezing point of water. So that would be on a cold winter day up in the mountains or something like that. And you can see that the speed of sound is pretty slow, relatively low on this chart. It's 331 meters per second. So the molecules in gases in general are far apart. So the speed of sound in any gas is going to be lower than it is in a liquid or solid. And also at lower temperatures, remember, the gas molecules are moving more slowly. Remember, higher temperatures means more thermal energy, more motion of those molecules. So if the molecules are moving more slowly, they will take a longer time to bump into their neighbor molecules. So as a result, the speed of sound is relatively low. You can see that air at room temperature is a little bit higher. It's 343 meters per second. This is due to the molecules moving faster at higher temperatures. Now, helium is interesting. Helium gas is very light. Of course, that's why they use it in helium balloons. And because of those lightweight molecules, they can move faster and react faster. They have less mass, less inertia. And so as a result, the speed of sound in helium is about 3 times higher than it is in air. And interestingly, this is why if you ever breathe helium out of a balloon, you can make your voice sound really high pitched. And the reason for this is the sound waves inside your vocal cords and voice box move 3 times faster, and that creates frequencies that are 3 times higher. And remember, higher frequency means higher pitch. So that's why you hear your squeaky chipmunk-like voice if you breathe and talk with helium. Oh, and by the way, it's not on this chart, but I've seen a demonstration where somebody breathes argon gas, and argon is a heavier gas than air. And also it's harmless because argon is one of the noble inert gases. Like helium, or it doesn't react with our body, so it's safe for short periods of time at least to breathe. So anyway, I've seen people take a breath or a whiff of argon gas, and it gives them a very low voice. They sound like Darth Vader. Even women or girls that have high voices can make their voice sound extremely low. All right, going down the chart here, we see liquids are next, and liquids have much higher speeds of sound. This is just because the molecules are closer together. They can interact with each other much more quickly. They don't have to move as far to bump into their neighbors. And then finally at the bottom are solids. And because solids are tightly packed atoms and molecules, they react very quickly when there are vibrations in a solid. So the speeds of sound are very fast. In solids. You can see some of these, and I put here's diamond down here, has the strongest bonds of any substance, and therefore it has a very, very high speed of sound, something like 12,000 meters per second. All waves reflect off of surfaces when they encounter a surface. And sound waves are included, and for sound waves we call this an echo. So an echo is a reflection of a sound wave off of a surface. So in this example here, here's the boy, and he claps his hands. So the sound wave travels distance d to this mountain here, and it bounces off, and then it comes back the same distance, d again, and he hears it sometime later. So suppose the boy hears his echo 4 seconds later. How far away is the mountain? So this is a way that we can use sound as a sort of an echolocation device to measure the distance to a faraway surface. So we know that velocity or speed is distance over time. So the distance that the sound wave travels is actually 2 times this distance, because it has to go there and it has to come back. So the total distance it travels is 2d, and the time is t. All right, so what we're going to do here is we want to know how far away is the mountain. We want to figure out what is d. So we're going to solve this for d. So we can multiply both sides by t and divide by 2, and we get distance is equal to vt over 2. Speed of sound, we can use 340 meters per second. The time was given as 4 seconds, and we have to divide that by 2, so that comes out to be 680 meters as the distance between the boy and the mountain. Echoes have lots of other applications that are, some of them are very important. For example, ultrasound is a non-invasive diagnostic technique where a medical technician can use an ultrasound transducer to send ultrasonic sound waves. I mean, we can't hear them. They're higher in frequency than our ears can hear, and it'll send them into our bodies, and they bounce off of different tissues and organs. In this case, it's a human fetus, and we can actually make an image on a computer screen to see the inside of our body. So that's pretty cool technology. Sonar is used by boats and ships, and basically it sends sound waves down, and they bounce off the bottom of the ocean or the lake, and they come back, and the software allows the people in the boat to basically tell the depth of the water. And now more sophisticated sonar systems can actually map out the structure of the bottom of the ocean or lake, and you can see that on a screen. And for example, this is how the Titanic was discovered, something like 13,000 feet below the surface, by using sonar like this. Bats have an amazing sense that we don't have, and it's called echolocation. They send out sound waves. They're ultrasonic to us. We can't hear them. And they bounce off insects, and they come back, and the bat can interpret those echoes. And actually, I think, biologists believe the bat's brain is able to form almost an image from these sound waves, which is something, we can't even imagine what that would be like, to be able to see sound. But by doing this, they can hunt at night, and they can basically detect insects that would be invisible to any other animal in the dark. Some of the older cameras used autofocus based on ultrasound. They would send out a sound wave, it hits the subject of your photograph and comes back, and it measures the time distance there, and sends a signal to the lens to focus depending on this distance here. One of the most fascinating phenomena of sound is the so-called Doppler effect. The Doppler effect is a change in frequency due to the motion of the wave source or receiver. And I'll leave the explanation up to the video. But basically, when you have a source of sound like a car, or let's say a fire truck with its siren going, the observer over here will hear a different pitch of sound as the observer over here. Because what's happening is, as the sound source here is moving towards this observer, the truck is basically chasing its own sound waves, and they tend to bunch up closer together, resulting in a higher frequency. On the other hand, conversely, for this observer over here, these sound waves are moving back towards him or her, and since the sound source is moving to the right, these sound waves are spreading out in space, and therefore as they arrive here, they are arriving at a lower frequency, so you hear a lower pitch. So this leads to a very fascinating effect called the Doppler effect. So let's go ahead and watch a couple of short video demos that will explain the Doppler effect.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Related to the Doppler effect are shock waves and what are called sonic booms. So this is these are just some diagrams here showing that we have in the middle here we have an object that's producing sound. So that, again, this could be a whistle or a car with a horn going or whatever. And in this first picture here, the speed of the object is 0, so it's at rest. So the sound waves are coming out basically in circles, and these circles are expanding at the speed of sound in all directions. You can think of them like bubbles, right, of representing the sound waves. Now, if the object starts moving to the right, like in this picture, all right, what we've got now is the Doppler effect. We see the sound waves bunched up in front and spread out behind. And this holds as long as the speed of this object is less than the speed of sound. But as this object gets closer and closer to the speed of sound, it eventually reaches the speed of sound, which is called Mach 1. And what happens now is the object that's producing sound is traveling as fast as the sound is trying to leave the object. So the sound waves are all piled up on top of each other, and this is called the sound barrier. It's a region of high pressure due to all of these sound waves just stacking up on top of each other. And it was a technological challenge to build military aircraft that could reach and break this sound barrier, and it was finally done famously by test pilot Chuck Yeager in 1947 in the X-1 experimental aircraft, and it reached and exceeded a speed of 760 miles per hour and broke the sound barrier for the first time. Now, what happens if you keep going faster and faster past the speed of sound? For example, what if you go Mach 2 or Mach 3? That would be 2 or even 3 times as fast as the speed of sound. Well, what happens then is, since you're out running your own sound waves, you're sort of leaving your sound waves behind you, and there are these expanding bubbles. But along the wave front of these expanding bubbles, where they all sort of stack up, there is a what's called a shock wave. And again, this is a region of high pressure because of all these wave fronts piled up on top of each other. And this shock wave travels away from the object here at the speed of sound. But when those shock waves reach the ground, like let's assume this is an aircraft that's going at Mach 2, it's going to produce a shock wave which we call a sonic boom. When the shock wave hits the ground, it sounds like an explosion, and it carries enough energy that it can actually break windows in buildings. So for this reason, it is not allowed to have an aircraft travel at more than the speed of sound over populated areas. Here are some interesting pictures of shock waves. This is a rifle being fired. You can see the bullet out in front here, and there's the shock wave due to the bullet traveling, and then also from the high amount of pressure coming from the tip of the rifle here, we see this bubble of expanding air, basically. This is the shock wave, and this is the crack that we hear when a gun is fired. This is the loud sound that we hear. It's due to that shock wave. This is a close-up of a bullet going at Mach 1.5. So again, this means it's traveling at 1.5 times the speed of sound. And you can see that out due to the tip of the bullet here, it's creating this shock wave here, and there are other shock waves coming off the sides of the bullet. And also, you can see some turbulence, which is kind of interesting, in the air behind the bullet. You don't have to go super fast to create a shock wave. As long as you're traveling faster than the speed of the wave, you create a shock wave. So here's this little duck swimming in a pond, but the duck is swimming faster than the waves that it creates, because waves in water, of course, go very slow. So as a result, the duck leaves the shock wave, and this is called a wake, and we see this behind a boat as well. All right, and finally, this is an old picture from a nuclear bomb test, and you can see the shock wave. There's actually two here. This is from the blast, and you see another one going through the water. You can see some ships here. These are not manned ships. They're just empty ships that were used to test the power of this explosion. But this is the expanding shock wave that is traveling through the water here. Here's a couple more interesting examples of shock waves. As an aircraft breaks through the sound barrier, there's a shock wave, which is high pressure that's formed, but behind the shock wave is a region of low pressure, which causes sudden expansion of the air. And when the air expands, it cools. So this rapid cooling of the air causes condensation of water vapor in the air, and it forms a vapor cloud. So you can see this really interesting vapor cloud, and this is the actual shock wave. You can see that shape, that kind of conical shape coming off of the aircraft here. There's even a small one coming from the cockpit of the airplane here. But this is just a region of low pressure behind the shock wave where the air is expanding and expanding so quickly that it cools and condenses the water vapor in it, forming that cloud. The last thing we're going to look at in this chapter is wave energy and intensity. So we noticed that, remember, our definition of a wave is that it's a disturbance that travels through a medium and the wave carries energy. So the main kind of concept of a wave is that it transmits or transfers energy from one place to another. So wave energy is the amount of energy in joules that the wave contains. The wave transfers this energy as it moves. Sound waves transfer energy, any kind of wave, water waves, a wave on a rope, and electromagnetic waves like light coming from the sun as well transfer energy. Now wave power, remember power is the rate of energy transferred. So the wave power is the number of joules per second or watts that the wave is transferring. So there's a nice sort of model to visualize how waves transfer energy, and that is this concept of what's called a plane wave. And if you think of a bunch of individual waves like this, and they're all in phase, and in other words, all their peaks are lined up and their troughs are lined up, then this region here, the shaded region, this is called a wave front. where all the crests are. So all the crests line up here, and this plane is called a wavefront. There's another wavefront here that corresponds to this crest, and a third wavefront over here. So these three wavefronts now are moving. In this picture, they're moving from right to left. These wavefronts are traveling at the speed of the wave, you know, if it's sound wave or light wave or whatever. With this idea here, we can think of each of these wavefronts as carrying energy, and these sheets of energy are they're basically approaching some surface here, and so we can define what's called the wave intensity at this surface. Wave intensity, I, is the wave power per unit area. So it's sort of the energy density. It's the rate of energy per square meter that reaches a surface like this. So wave intensity is the power of the wave divided by the area. So we have power, remember, is joules per second, or watts, and the area is measured in square meters. So just to give you an example, sunlight, especially during the summer and at midday when the sun is high overhead, delivers about 1,300 watts per square meter to the Earth. Now think about that. What that means is sunlight is bringing 1,300 joules every second to every square meter on the Earth. Okay, so this is obviously a lot of energy, right, that's coming to the Earth, and this is why solar energy is such an important energy source, right? The sun is this basically unlimited supply of energy for the Earth. Our last slide here in this chapter has to do again with the intensity and rate of energy transfer, but this we're going to talk about for sound, and so this has to do with the loudness of sound. So for typical human hearing, the threshold, meaning the softest sound that we can hear, is an intensity of about 10 to the minus 12 watts per square meter. Now this is an extremely low intensity. Our ears are amazing devices, and they can detect extremely low power waves. So this intensity, this threshold, is I naught, all right? And remember, this number here, this is 1/trillionth of a watt per square meter. So that's the quietest sound that we can hear. All the other sounds, of course, are going to be louder, and we measure the loudness of sound using units of decibels, right? The decibel is abbreviated lowercase d, uppercase b. So what is a decibel? Well, the way we calculate the sound intensity level in decibels, which, by the way, uses the Greek letter beta, is we take 10 decibels times the logarithm of the intensity of the sound, I, divided by the threshold of human hearing, I naught, which is this number right here, 10 to the minus 12. And that will give us the sound intensity level in decibels. So let's just work through an example here to see how we can use this. So how many decibels is a sound with intensity of 2 times 10 to the minus 6 watts per square meter? So here's our formula for beta, and what we're going to do for I here, we're going to plug in our intensity, which is 2 times 10 to the minus 6. I naught, remember, that's this number up here, that's the threshold sound, that's 1 times 10 to the minus 12. All right, now this looks like a mess here, but actually you can do this in your head. 2 divided by 1 is just 2, and here 10 to the minus 6 divided by 10 to the minus 12, well, remember, whenever you divide by something, you bring it up to the top as a reciprocal. So this is the same as 10 to the minus 6 times 10 to the 12, and all we have to do is add minus 6 to positive 12 to get our exponent, which is minus 6. All right, so I'm sorry, anyway, I think I had an extra minus sign in there. But 10 to the minus 6 divided by 10 to the minus 12 is 10 to the minus 6. All right, you can take this number and subtract the other. Okay, so here is on our calculator, we're going to plug in 2 times 10 to the minus 6, and we're going to take the logarithm of that. All right, so there's a button on your calculator that says log, and the logarithm of this number is 6.3, which we multiply by 10 decibels to get our final answer, which we were looking for. This sound with this intensity would be measured at 63 decibels. So this table here shows some common sounds that we hear and the number of decibels. So for example, in a quiet room, if you have good hearing, you can hear someone breathing at about 3 meters away, and that would be a sound of about 10 decibels. A whisper at 1 meter away is about 20 decibels. Talking, normal, let's skip down here. So normal conversation at 1 meter is something like 60 decibels, a vacuum cleaner 80 decibels, and you can see it keeps going up. Notice that this scale here, it's certainly not linear. This is a logarithmic scale. This goes up by factors or powers of 10. Okay, so, but notice some of the loudest sounds that we can handle, for example, a rock concert, around 120 decibels, and once you get above that, the sound becomes painful and can actually damage your ears. So, that is our lecture from chapter 15 on waves and sound. I will see you in the next chapter shortly. Goodbye.